record button. Okay. How is everyone? Excuse me. Hi, Devon. Hi, Gauli, Sebastian, Saeed, Elena, Evelyn, Jaslyn, Carla, Ricky, Elena, Sean. Thanks for keeping your cameras on, some of you. Thank you. Appreciate that. Any news from anyone? Any comments? Oh. I filled the board, right? Yeah, I did. Yeah, the flowers are beautiful, but then the way the pollens interact with some of us is not fun. I don't know if anybody else is having allergies. I'm really stuffed up. The flower that Jasmine has taken the picture in front of, I think there's a little beautiful tree. That the picture is making me feel allergic. I'm just kidding. It looks like it can give me some sneezes. Hi Alexia, hi Roxana, hi everybody. One more minute, we'll discuss NMR and then we'll just discuss NMR today. I don't think it's going to be anything else. I don't think we're going to be switching to any other discussion. Okay. One more minute. I don't know what's going on with my throat. We'll start with that equation that we had written, delta equal to H nu H multiplied by gamma BE divided by 2 pi, and we'll go from there. We'll start with that and then keep expanding on the concept. Hey, Michael. Hey, Adil, Isaac, Yasmin, Varun. Who else is here? That's pretty much it. Okay, let's move to the board. Okay, I might end up switching to the PowerPoint. Okay, there is a text. Cyclic step code. Oh, oops, that's not good. All right, let's move to the board. And I hit the record button. Something weird is happening with my Zoom because the morning class was supposed to be auto record. It didn't do the auto record. So I realized it printed. Okay, let's move to the board. The sun is pretty bright outside, but I think the light is still kind of diffused. If you guys see any glare, I don't think there's any glare, but if there is glare, let me know. All right, let's keep going. So I'm going to write down kind of small here. So we are 128 B, and today is 13, 4, 13, 21. I just want unobstructed board space. So 128 B, and we're still talking about NMR. Okay? I don't want to make any promises about how much I'm going to cover because I know that every time I do that, I jinx something. Okay, so the formula, I'm not going to go back in the past too much. So the energy, the relaxation energy, E beta against B0 with RF, after the RF is working, radio frequency, that minus E alpha, the lower energy, E alpha is with B0 with the external magnetic field. That can be written as, I'm going to use different color coding because I'll take the pain to do that. H multiplied by mu, and it's going to be equal to H multiplied by gamma. What color should gamma be? How about green? That's my gamma. That looks horrible. That doesn't look like gamma. That looks horrible, but forgive me, that's my gamma. multiplied by BE. BE, let's make it a different color. Purple. Ooh, so excited. BE is the effective magnetic field felt by the nuclear magnet from the main magnet that the instrument has, the B0, that's penetrating through the electronic cloud. And I'll draw a little cartoon picture, okay? Divided by 2 pi. Okay, and this can be also written as H multiplied by my famous gamma multiplied by B0, the main magnetic field, subtracted is the local magnetic field that's in the electronic cloud. Okay, let's pick a color for that. This color. Yes. Okay. So it's important because I really want you guys to understand this. Okay. And let me just redraw this business here. You know what? Let me just move it a little bit to the left. BE equal to B0 minus BS. Okay. So we have Mother Earth. You know what? Let's not use any metaphor. Bad idea. Nucleus. Okay, you have the proton. That's the proton, positive charge, right? And you have the electronic cloud. That's the electronic cloud, and this is where one of the electron is, that the only electron. Okay, and that whatever the magnetic field generated by the electronic cloud is BS. This is BS. That's in the cloud, and then we have the magnet where the whole molecule is sitting. This is B0. Let's say, I don't know which direction the B0 is pointed at, but let's call it B0. And this is the external magnetic field. Okay, that's B0. So B0 is trying to get through the electronic cloud, and whatever is going inside, that is being felt by the nucleus. That's BE. Okay, so BE is the total minus the shield is BE. That's the effective magnetic field. So sometimes when the book writes B0 here, that's not entirely correct. They're trying to introduce the concepts to you, so it's not, they're not deliberately doing a mistake. I don't think the author is delusional. Author knows exactly what's going on, but they're just setting up the stage slowly. But I would rather put BE here than calling it B0. The B0 is slightly flawed. Okay. And one of the critical points, as I have mentioned in the past, is this is the BS is very important. It sounds funny, but this is very, very critical. Okay, because if the thickness of the electronic cloud didn't vary, and if it didn't make an impact, and if human beings, the chemists or the scientists could not figure it out and use it to their advantage of getting different signals, different delta E values for different protons, different hydrogens, then this field would not have developed. Okay, so that's very critical. That's very important. That's a pretty bad line, not straight at all. I don't know if it is straight now. It's a little bit better. Okay, this is the main magnet. It's sitting in the magnet. Okay, the molecule is sitting in the magnet in a little sample. All right, so that's important. So let's say, so the bottom line is, let's draw like a fake molecule, like not like a fake molecule, but a real molecule. But we're going to be using it as a representative of different types of, hydrogens. Okay, so let's say a molecule. So this is our formula. Let's say we introduce ourselves to like a real spectrum. What does it look like? And then while we learn the real spectrum, we're going to pick up a few more, important aspects of NMR spectroscopy. Okay, so that's the formula and everything else. All right, so let's look at a molecule that looks like this. Some molecule that has 3 different types of hydrogen. So how about this? Carbon. Let's use a real molecule. Carbon with a carbonyl, and this guy has 3 hydrogens here, and then it has an oxygen, then it has a carbon with 2 hydrogens, and then it has one more hydrogen, one more carbon, and it has 3 hydrogens. Okay. As we learn about equivalency of hydrogens, like basically looking at a molecule or looking at a structure, there is a motel and it's got 5 rooms. Okay, and imagine that the end of one alley is kind of like this, and it has 2 rooms like a V, like a little split at the end of an alley, and there is a room here and there is a room here, and the rest of the motel is kind of straight, so it's pretty symmetrical. So from in that motel, this room and this room are almost like mirror images, and they're almost like identical. So if you have twin nephews or twin nieces and they want identical room, maybe you can put one here and one here, and they're going to be happy. They're happy because they got same room. The other person didn't get a better room or a worse room. Everybody's happy. So learning equivalency and learning kind of using the concept of symmetry to figure out like which hydrogens are kind of similar and which hydrogens are not similar. That's called, figuring out the equivalency of hydrogens or other elements. Okay. So in this particular molecule, this molecule is called ethyl acetate. It's an ester. Ethyl acetate. That's the ethyl group, and this is the acetyl group. So this is ethyl acetate. It's an ester. This functional group is called an ester group. Okay. How many total number of hydrogens does ethyl acetate have? Count the hydrogens and tell me, what's the total number of hydrogens?
8.
8. 8 hydrogens altogether. 3 plus 2 plus 3. And I have already color coded it because I don't want us waste a lot of time figuring out equivalency. You should be able to kind of pick it up on the fly. Okay. How many types of hydrogens are present in the molecule?
3.
3, right? Okay. So that's one type. Okay. That's a methyl group. Methyl is CH3, METHYL. Okay. I'm not undermining your knowledge or your brilliance, but then sometimes we forget. Okay. That's one kind. That's the second kind. And that's the third kind. Okay. Now I'm going to test your knowledge. There is the, I don't know how clear the colors are on your screen. That's black, this is blue, and this is green. Okay, black, blue, and green. Okay, ready? I did push the record button, right? Yeah, I did push the record button. Think about it for like a minute. If I ask you between the three kinds of hydrogens in this molecule, which kind you think has the thickest electronic cloud, which kind has the thinnest electronic cloud, and which one is in the middle? Let me just number them. Let me number them using like a neutral color. So let's call it hydrogen number 1, let's call it hydrogen number 2, and let's call it hydrogen number 3. 1, 2, and 3. The question is the following: which one has the thickest electronic cloud, okay, maximum BS, okay, and which one has minimum BS? Sounds funny. I can't control my expression. Which one has thickest shield? Which one has the thinnest shield? Think about it for a minute. Don't rush. Take your time. Use the force. Let the force be with you. Oh, I wish I had some coffee with me. I'm thirsty and hungry too. If you think you have an answer, just spit it out right now. You say that I want to answer, then go from there. Look at the electronic environment. Think about that situation and use your, I'm not going to get into the real nitty-gritty details, but I just want you to kind of develop a feeling. After 128 day, you should already have that feel. Like this environment looks pretty bad, pretty electron situation doesn't look very good. So 1 black, 2 blue, 3 green. Which one you think has the thickest electronic shield around their nucleus?
3.
Who said that?
I did.
Sebastian. Sebastian says, okay, hydrogen 1, hydrogen 2, and hydrogen 3. Sebastian says this has the thickest, that's my S, thickest electronic cloud. So, or you know what, let's write more professionally. Let's say this is the BS column. Okay, so you're saying this guy has the largest BS, the local magnetic field. So that's the largest. Between 1 and 2, the black hydrogen versus the blue hydrogen, which one should have the smallest number for BS? Which one should have the thinnest cloud? This guy or this guy?
I think it's number 2.
Number 2. You're saying that number 2 should have the smallest value for BS, and this one should be intermediate. Okay. I'm not complaining. I'm not criticizing. I'm just trying to keep a straight face so that I don't give away how I feel about your answer. Anybody wants to explain one of the numbers, 2 or 3? Like Sebastian thinks that should be the thickest cloud and that should be the thinnest cloud. Why? I want someone else to answer. Pick this one. Why do you think, you know what, pick number 2. Why do you think number 2, the blue hydrogen, should have the thinnest cloud around the nucleus?
I think they have the thinnest cloud because they're closest to the electron withdrawing oxygen atom.
What's the electronegativity of oxygen? Who remembers? Somebody else. This is a teamwork. Come on. Who remembers oxygen's electronegativity value?
3.5 or 3.44.
I'm not going to get down to that kind of precision. Then, so 3.5 is pretty darn good. So 3.5. What's the value of carbon's electronegativity? Somebody who hasn't spoken today.
2.55.
2.5.
2.5 is good. Who was that? That was Carla with the dog nose upside down. What's the value for hydrogen? Who remembers?
2.1.
Okay. 2.1, 2.5, and 3.5. So it's really pulling hard, right? So it's pulling pretty hard, and it's pulling electron density from here. So number 2 has the thinnest cloud, right? What do you think about this guy? Is this group going to be making electron? Is carbonyl, if I consider it as a separate group, is carbonyl an electron withdrawing group or an electron donating group? Somebody who hasn't spoken today. Is that an electron withdrawing group or an electron donating group?
Electron withdrawing.
Varun, why?
Because it's also like really close to the electronegative oxygen,
Okay.
like the one in the middle.
Okay, so you're saying that this is going to pull in that direction, and that's probably going to be felt here. Something like that. Is there another effect that can happen using the double bond? I don't want to get distracted right now because, I want to stay focused today. So remember, maybe remind me sometime later when we talk about carbonyl chemistry, we can discuss resonance effect. I don't know how much you have learned resonance. I want to go over resonance one of these days in April before it's too late. Just one more time, okay? So yes, so it's got that inductive effect. Inductive effect is the effect that's that emerges due to the difference in electronegativity. More electronegative, the bond gets polarized toward oxygen. That's inductive effect. Usually we use the uppercase I to kind of like label it. Okay, minus I because it's withdrawing. If it is pushing electron density like here, carbon is more electronegative than hydrogen. So the push is in this direction. So methyl group or an alkyl group has plus I effect. Oxygen has minus I because it's subtracting electron density from the neighborhood. It's adding electron density to the neighborhood. So alkyl groups have plus I effect. Halogens, oxygen, they have minus I effect. This group also has a minus resonance effect because the pi bond can move up and pull electron density if the neighborhood permits. Okay, So it can do that. Yeah, this is great. Okay, this is perfect. So this guy is next door to a sigma situation, like sigma bond. Nothing different than carbon. And carbon, they both have very similar electronegativity values. So this guy is probably going to have the thickest electron cloud. That's fantastic. This is great. Okay, we are going somewhere. Okay, all right. Now let's draw like a fake NMR spectrum. Okay, how will an NMR spectrum look like? And I want to introduce, which is always my, like almost like my fear, like, you know, how long it's going to take me to describe the x-axis. Hopefully we can do it fast today without spending way too much time. If this is your NMR spectrum, okay, let's say this is your h½ by the proportions or aspect ratio is pretty screwed up. So forgive me. I just wanted this to be kind of long so that you guys can see it well. Okay. So this is your NMR spectrum. NMR spectrum of this molecule. Okay. Down along the x-axis, with what we are plotting, we are essentially along x-axis, we are essentially plotting delta E values. Okay. X-axis. That's not the end of the story, but I need to spend more time explaining the x-axis. So I'll get there in a second. So this is x-axis. We are plotting delta E. And delta E is different for different hydrogens. Why is it different? Because BS is different. Why BS is different? We already discussed it. Electronic environment. If BS is less, BE is more. If BS is more, BE is less. Make sense? Right? So if BS is big, then delta E is small. Make sense? If BS is small, then BE is large and delta E is large. Connect the dots. It will be necessary in the next quiz and the final exam. Okay. So the way the delta E is plotted is, generally speaking, in all spectroscopy, right side has less energy, left side has more energy. Energy goes up from right to left, like we saw it in NMR IR spectroscopy, right? 600 or 400 to 4,000, 400 centimeter inverse to 4,000 centimeter inverse, right? More energy to the left. IR radiation is less here, IR radiation is more here. So same here. So the delta E value, I know some of you are probably, it's probably bothering you because it's not really delta E, but we will get there in a second. Okay. I was thinking about something, so I wrote that. I jumped. My mind jumps. You know, that happens with typing. Sometimes you're typing color, COLOR. When you are at L, you're already thinking about R. And sometimes I would replace the L with R. And you need to slow down. So delta E, okay? Delta E is often measured in hertz. I'll explain what that is. Delta E is going up in this direction. So delta E value is less on the right and more on the left. Okay. And often delta E is measured in hertz. It's a unit, it's a unit of energy. What does it mean? It means number of waves, sinusoidal wave, like radio wave. In this case, it's radio frequency. The radio frequency that you're using to basically mess up the magnets in the opposite direction to cause delta, the E beta, to create the high energy state. that radio frequency's number of waves per cycle per second is hertz. So it's measured in hertz, it's number of waves per second. It's a pretty standard unit of energy, hertz. Not much energy. 1 hertz, a few hertz is not that much of energy. Okay. Radio waves are the weakest wave. We talked about it, right? Radio waves are used in radios, radio waves are used in motion detectors, radio waves are used in radar detector, in radar, old-fashioned radar, not the laser radar. Okay, so that's that. So this is in hertz. It's going to change. The real x-axis unit is going to change. So this is, I'm just setting up the storyline right now. Okay. Imagine this is delta H. Okay, less energy on the right, more energy on the left, and there will be different peaks. Tell me between the hydrogen 1, hydrogen 2, and hydrogen 3, the black hydrogen, the blue hydrogen, and the green hydrogen, which hydrogen will show up on the extreme right and which hydrogen will show up on the extreme left? Black, number 1, blue, number 2, and green, number 3. Which hydrogen should be on the extreme right of the spectrum? I'm going to use it as a proof of concept, not accurate to the scale. Okay, I'm just going to space them out, even though they're not going to be like that in the real spectrum, just for you to understand it in a better way. So which one will be here, which one will be middle, and which one will be on the extreme left?
Two would be on the extreme left.
You think the blue one will be on the extreme left?
Yeah.
It's supposed to be a line. It depends on the spectrometer's resolution, how expensive the magnet is. I'm just going to draw it like a little triangle. Okay, let's say this is number 2, you said. Okay, Sebastian, you're done with your answer. Somebody else answer. Where would there will be a peak here and there will be a peak here? Which one is which? Which one is 1 and which one is 3? Somebody else, somebody who hasn't spoken today. Pick up one of the peaks and tell me that this hydrogen is going to be in the middle and this hydrogen is going to be on the right. Or you can answer just one, and that's basically tells the whole story. Somebody who hasn't spoken today.
Hydrogen 1 is going to be in the middle.
Hydrogen 1 is going to be in the middle. Okay. That means hydrogen 3 is going to be on the right. What color is hydrogen 3? Green. Okay. What do you guys think? They're blowing smoke or they're talking some sense? Sebastian and Jaslyn. Does it make sense? Can you guys relate to their answers being correct or incorrect? Or you think this is totally wrong? Anybody wants to support them or argue that this is wrong? I'm having allergy problems, so I'm going to stand outside the camera's periphery and make myself a little more comfortable. Sorry about that. What do you guys think about the assignments of the three hydrogens? Right, wrong, ugly, terrible, pretty good? Connect the dots. Why did Sebastian say that number 2 is on the extreme left? What does that mean? Extreme left means high energy or less energy? Somebody who hasn't spoken today. Is this the delta E value? Which of the 3 peaks, 2, 1, and 3, has the largest delta E value? Sorry?
largest delta would be 2 since it would have the smallest BS.
So this one has the largest delta E value because in the NMR spectrum and most spectra, most in spectroscopy, left is more energy, right is less energy. Okay, UV visible, IR, NMR. Okay, this one has the smallest delta E, largest delta E. Connect the dot. This is very important. In the final, this is going to be carrying a lot of like point values. This can be the differentiator between A and B or B and C or C and failing. Okay, I hope not. So smallest delta E, largest delta E. Largest delta E means which one has thinnest cloud, number 2 or number 3. I'm just kind of going back and forth so that to reinstate the concepts. Which one, number 3 or number 2, should be red color. Number 2 or number 3, which one has the thinnest cloud?
2 has the thinnest cloud.
2 has the thinnest cloud. Let's go answer as fast as you can. Thinnest cloud. Which one has the thickest cloud? 1, 2, or 3?
3.
3. Which one has largest delta E?
2.
2. Which one has the intermediate value for effective magnetic field? Intermediate. 1. Okay, very good. Okay, so far so good. Remember what we just discussed to your heart until you pass, finish this course. Okay, this is very important. Okay, all right. So in the NMR spectrum, before we get to this annoying discussion about the x-axis, something has to be done to the delta E value. We'll discuss it. So you realize that this is very important. This is what is creating 3 peaks instead of 1 peak. Otherwise, you would have gotten only 1 peak from all the, how many? 8 hydrogens, right? Okay, so that's important. So a few more definitions. On the NMR spectrum, the left side and the right side, there are 2 names for them, okay? The right side is called not uptown, it's called upfield. The left side is called downfield, okay? So this direction is called downfield. Keep it in mind. More energy, downfield. Less energy is called upfield. Okay. Left side, thinner cloud. Thinner electron, I'll just say electron cloud. You get it, electron cloud. I'm not going to write everything. Okay. Let me just move these numbers down here. This is 2, this is 1, and this is 3. I need that space up here. Okay, now I can write electron cloud. Okay. This direction, thinner electron cloud. That direction, thicker electron cloud. Make sense? The right side, if I have to choose the word shielded, think about the Death Star and the shield. If I have to use the word shielded to describe the right side or the left side, which side shall I call shielded? Right or left?
Right.
Why? Who is this? This is Andre. Because yeah,
thicker
go ahead.
cloud.
Thicker cloud, absolutely. Yeah, there is nothing much to talk about. Yeah. So the right side is called shielded. Should be a different color. Am I running out of color? 1, 2, 3, 4, 5. Yes, I'm running out of color. So let it be pink. So what should be the opposite word of shielded? What did the scientists come up with the word? It's not, it's something else. Does anybody know what that is called? Michael, you cannot answer. It's not shielded. So what word do we use to describe the left side? Anyone wants to take a wild guess?
De-shielded.
There you go, de-shielded. This side is called de-shielded. Very good. I don't think I'm missing out anything. Downfield, upfield, thinner cloud, thicker cloud, de-shielded, shielded. I think that's it. Okay. Before I start talking about how fat the peaks are, that's probably very inappropriate these days, but I'm just calling the peaks fat. So I guess it's okay. Okay. So before we do that, before we start talking about that and splitting and all that stuff, let's talk about what I've been avoiding all along. Let's talk about the x-axis. But before we do that, let's look at the formula one more time. But you know what? Let me just shut up for like a minute and let you guys kind of sync with all the information up here. I'm going to just sit down at my desk and not in your vision, in your periphery. Just make sure everything makes sense, what you have learned so far on the board. I think the board is decent. It's not too cluttered. Just if you have any questions when I stand up again, then you can ask me. Half minute. Close to a minute. Any questions so far? Is it clear? I want you guys to understand, if you're taking 128B from me, I really want you to get NMR well. Not to the level of Michael Coppage, but then, you know, to my high level. Whatever I know, I'll try to teach you. So far, so good? Make sense? Okay. So as far as the formula is concerned, right? As far as the formula is concerned, there are a few factors that affect the value of delta E, like where you might see the peaks. Delta E depends on, well, pi is constant, unless we go to a different universe, maybe H is constant. Gamma is an intrinsic property of different nuclei. So gamma is constant for hydrogen. As long as we're dealing with hydrogen, that number is constant. We don't have to mess with it. We don't have to worry about it. It's smaller for carbon-13, but that's a different story. That's a different challenge, different problem to solve. Okay, you need more sample. You need to have better, stronger magnet, etc., etc. Okay, that's not something that you need to worry about. What does BE depend on? Well, BE depends on two factors. One is the thickness of the electronic cloud. That's a property of the molecule. If you're dealing with this molecule, the shielding and de-shielding of the electronic cloud is going to be constant. It doesn't matter if the ethyl acetate you are dealing with is here in Fresno or in Maine or in New York or in North Dakota or in Siberia or in India or I don't know, Heidelberg in Germany or wherever it is. It doesn't matter, right? In Norway. So they are all constant. So this number is constant for that particular hydrogen, for that particular molecule. It varies. From ethyl acetate, if you take ethanol, the shielding, deshielding properties are going to be different. If you take bromoethane, it's going to be different. Everything is going to be different. Dibromoethane, 1,1-dibromoethane, that's going to be different. 1,2-dibromoethane, that's going to be different, right? So all these molecules are going to be different. Aromatic compounds are going to be acting differently. So they're all going to be different. The only thing is that, so you don't have to worry about that. B0 is a little problem because if you're in, sorry, I forgot to turn off my phone. B0 can be a problem, and that's going to affect your definition and your manipulation of the x-axis. If you're in City College, you have a magnet that's the strength of the magnet is 60 megahertz. This is hertz. Okay. These energies of these, the delta E's are measured in hertz, 1600, 2000, 5000, 500, 600 hertz, different types of different energies in that range. The main magnetic strength, they're in megahertz. Mega means 10 power 6, okay? Million hertz, okay? So if you're in City College, the strength of the magnet is 60 hertz. If you're here 12 years ago, the strength of the magnet is 200 megahertz. If you're here like 6 years ago, the strength of the magnet is 300 megahertz. Now it's 400 megahertz. We are getting a 600 megahertz. If you go to Berkeley, I believe it's 800 megahertz or gigahertz. So depending upon which magnet you're using, how rich the campus is or institution is, the geographic location, the delta E will be constantly changing with B0. B0 more, delta E more. B0 is, the value of B0 is less, the value of delta E is going to be less, right? So you will be constantly fighting with a number that's changing for these three hydrogens. That's not good. That's terrible. That's going to be that's almost like the current problem that the electric cars are having with different types of charging ports and charging stations. Okay, it should be unified sometime, but then it's not. So imagine that this is being developed here. It's being developed in one of the Asian countries. It's being developed in Europe, and everybody is defining the x-axis according to their magnet. Somebody has an expensive magnet, they're accordingly, setting it up. So what's the solution? Michael cannot answer. How can you solve this problem so that the numbers, these numbers are always constant irrespective of the strength of the magnet? How can we circumvent this problem? Anybody has any idea? So this is not it. So it's not just the energy of the relaxation energy that's being plotted. So that's manipulated further before we start plotting it. What do you think? What do you think we do? How can we make that number show up at the same position irrespective of the strength of the magnet? And the strength of the magnet, let's say B0 is 60 megahertz. Another option is 200 megahertz. Another option is 400 megahertz. Another option is 800 megahertz. Each time the value goes up, the delta E will be twice here. The delta E will be twice that much. And the delta E from between here and here will be like 4 times. So the values will be different. And the x-axis is going to be going through the roof and creating a lot of agony and anxiety and stress among scientists, NMR scientists, like Dr. Krishnan will be pulling his hair, figuring things out, adjusting the numbers when he's looking at the spectrum taken in UC Davis versus Berkeley versus here. I'm not laughing at his pain, but it's kind of fun to always make fun of a physical chemist and they do the same thing. He teases me and I tease him back. So it's always like a very friendly war. Okay. So what do you think we can do to that number so that we don't have to deal with this problem? Wherever we are talking about these peaks, the locations are always like this number, that number, whatever number. How can we circumvent this? What do you have in mind?
Proportionally or by percentages?
Say that again, Ishan.
Either proportionally or by percentages?
Percentages.
Or proportional.
Well, I think you
Like-
have the right idea, but you're not saying it the right way. You take the number, the whatever the delta is from here, okay, from the calculation, you know whatever number pops out, okay. You take delta E. Where is my blue pen? Oh, right here. Where is my purple pen? Okay. So that's not how it's done. So it's delta E. There is another aspect here. So what we plot here, we end up plotting here is delta E of the hydrogen, whatever hydrogen, let's say hydrogen number, the green hydrogen. So let's say the green hydrogen. The delta E of green hydrogen, I'm going to leave some room there on the right side. And then we put something down here. And this is definitely going to be in hertz. This number is going to be in hertz. Okay, that unit is going to be hertz. We're going to divide that number by something. What should we divide it by so that the resulting number is always going to be constant? I think Eshan had the right idea, but maybe you didn't articulate right. I'm just going to tell you. We're going to divide it by B0, the strength of the main magnet. Okay. B0 in megahertz. Okay. We are going to get to the ppm business in a second. Okay. I wish somebody explained it to me when I learned NMR the way I'm gonna going over. I would have really appreciated it. So much of my teaching inspiration were accumulated as I was at the receiving end throughout my life. Okay. Now there is a little problem. Okay. So how do we know, like, if we have a random compound, we are dealing with that here, and we are dealing with something else here. How, like we have like some control experiments, or we have some standards. We know that water boils at 0 degrees centigrade. We know ice melts at 0 degrees centigrade, and water boils at 100 degrees centigrade. Sorry, my bad. So we know those two numbers. And then when my temperature, after the Moderna vaccine number 2 was going up to 101, we kind of compare with respect to that in the Fahrenheit scale. Okay. So things like that. So we need something standard to compare where our molecules or different hydrogens are showing up, right? So we need a standard. So what we do is we use a molecule that has an extremely shielded proton or protons, and we keep that on the extreme right. It's getting very convoluted. I understand that the x-axis discussion is getting very convoluted and kind of lengthy. So I might be losing you in this discussion. If I lose you, you need to think about it and go through it in your mind alone, and maybe with your friends, and watch the video again and make sense out of it, because this is important. Okay, so these numbers, we cannot arbitrarily put these numbers. Okay, so we need to have some standard number or something that's going to be always showing up at certain point, and that's going to be your internal standard. Okay, so we're going to use this number, and we're going to subtract the delta E of a specific standard or internal control molecule. So we're going to subtract delta E of an internal standard. What color shall I use? How about blue? We're going to discuss that internal standard, and this is going to be in hertz. So we're going to discuss that in a second. Okay, so whatever the delta E relaxation energy of your hydrogen is, this hydrogen versus this hydrogen versus this hydrogen, that's going to be, we're going to be subtracting the delta E of another molecule that's going to be a standard, okay, which is going to have a super shielded hydrogen scenario setup, okay? And that's going to be kept on the extreme right, and we're going to always call that guy, the delta E that molecule comes up with, throws at us, we're going to always say that that's 0, okay? So that's going to be our 0. So we're going to discuss that in a second. So delta E, the relaxation energy of whatever hydrogen you are dealing with, minus delta E of the internal standard in hertz divided by the strength of the magnet in megahertz. So when you have hertz by megahertz, it essentially means this. It means you have on top hertz and down here megahertz. Megahertz basically means 10 power 6 hertz. Hertz and hertz cancel out. So it's basically by or per 10 power 6 by per mega, right? So it's essentially, it means 1 over 10 power 6. Therefore, it is called parts per million. That's the unit. It's not hertz. It's not any other bizarre unit. It means there's no unit. It's just per 10 power 6 per million. That's what it means. That's why the word ppm comes from. So this unit, as that cancels out, this is always, the unit is going to be called some number ppm. Okay, this is going to give rise to a number, because this B0 could be 60 megahertz, 200 megahertz, 400 megahertz, 800 megahertz, whatever number plugs in here, and whatever number you come from this calculation, from the subtraction, that's going to be divided by 400 or 300 or 1000 or 1200. If you're that rich, they're like multi-million-dollar instruments. And so it's going to be some number, and ppm. The ppm is parts per million. Parts per million. I want you to understand it. So I'm going to pause for 30 seconds again and make sure that you guys understand. I'm going to also take a snapshot of the board. I'm going to block the camera for a second, and we're going to go from there. One second. I'll just make sure you are following what we are discussing so far. Oftentimes we assume that our students understand ppm and the x-axis, but I really wanted to explain it going deep down in the concept. Like, this is how it happens, and I'm going to be testing your knowledge based on your understanding and learning from the Zoom lectures. So I do not really know if the book deals with it the way we are dealing with it, but hopefully it does. So however you can learn it, learn it. Any questions so far? I'm going to erase. Sorry, go ahead. Did anyone have a question? Okay, syncing well. You're following the lecture. Everybody who is even staying quiet here in the classroom. Okay, I'm going to assume that no answer means good. So let me erase this part. I don't think we need. Let's keep the molecule, because we will need the molecule. Okay, we'll keep the molecule. Let's erase this. And let's keep that. Let's explain what internal standard is. Well, it's not that difficult. It's pretty straightforward. Much more manageable than what we have been discussing so far. We're getting there. We're getting to the end. I'm seeing the light at the end of the tunnel for the NMR tunnel. Okay, so where is our black mark here? Okay, that's how far the camera goes, and that's how far the camera sees on the left hand side. Okay, so what's going on with the internal standard? So what I'm going to do is I'm going to extend it a little bit. And the internal standards can come in different shapes and colors, but the first internal standard that scientists came up with stayed on the extreme upfield region. Okay, I'm going to use a color that's going to stand out. How about red? So let's say that's a terrible line. Okay, I'm just going to draw like a triangle if I can. Okay, there you go. That guy is going to be your internal. Let's lift it up and start writing from the top. That's going to be your internal standard. And I want you to understand, this is my teaching philosophy. I want you to, those of you who care, I really want you to really understand what is going on here, okay? When we are deciding the internal standard, we can either place the internal standard in the middle of the spectrum or extreme right or extreme left. Would you like your internal standard to be sitting in the middle of the spectrum or at one of the two corners? What's more convenient for clarity in the future when you're dealing with different types of compounds? What's more desirable? One of the ends or in the middle?
An end.
And because it's going to stay out of your other peaks that will be emerging from your molecules. And the right side was chosen. And if you want your internal standard to show up as an extremely upfield signal, extremely shielded signal, right? So the hydrogen that you're dealing with, whatever the hydrogen you're dealing with in that particular molecule, it should have a pretty darn shielded electronic cloud. Okay, if you want your internal standard to show up on the extreme right in the shielded region, it's going to be extremely shielded. If you want that, that's your desire. If you want it to be super shielded, like super spreader. If you want it to be super shielded, it's going to be on the extreme upfield region. You want your electronic cloud to be as thick as possible, right? All right. And it has to have, the internal standard must have some other properties that we're going to discuss. I will be testing your knowledge in the quiz and in the final. Okay. All right. So that's that. So super shielded. So the hydrogen must be attached. It could be attached to a nitrogen. It could be attached to some crazy stuff like, I don't know, sodium hydride. But sodium hydride, there will be a problem. Sodium hydride is super reactive. There has to be some other properties. It should be pretty inert because you're going to be throwing all kinds of molecules, biological molecules, synthetic molecules, natural molecules, intermediates, all kinds of molecules. So one property of the internal standard is that either it should not be messing with your molecule, it should not be reactive. So sodium hydride, hydrogen is more electronegative than sodium, so it should be very shielded. But the problem is sodium hydride is going to probably react with pretty much everything it comes in its path with. Okay, bad idea. So you want, and you can have ammonia. Well, ammonia, nitrogen is more electronegative than hydrogen. It's not going to be shielded. So in order for the hydrogen to be shielded, let's say that we choose a molecule that's connected to a carbon. Okay, it's some kind of a CH. And the carbon, maybe the carbon can be hooked up with something. Maybe the carbon can be hooked up with something we don't know, that's going to be less electronegative than carbon. What's the advantage? Well, the advantage is if it is less electronegative than carbon, then carbon is going to pull electron density toward itself, and as a result, maybe the hydrogen will be very shielded. Maybe it's going to have a thick shield, right? So other options, other properties of the internal standard. Number one, shielded. That's number one requirement. Number two, second requirement, inert. Inert means unreactive. You don't want it to mess with your molecule. Unreactive. Give me some other properties. What should be some other properties of the internal standard? Anything else comes to your mind when let's say you're trying to commercialize, you're trying to come up with an internal standard that's going to be a commercial product, and you are starting up a startup company, and you're going to be selling solvents for NMR and stuff like that, and you're trying to come up with an internal standard. What else should be crossing your mind if you have a good sense of business?
Like how abundant it is?
Say that again. What did you say?
How abundant?
Abandoned. Yeah, sure. Great point. Something else.
Cheap?
Very important. Sometimes it's not cheap, but sometimes you have no choice. Okay, that's why we look for grants. Okay, inexpensive. And something else comes to your mind, something else like it should not be toxic, maybe safe. One other point, which may be difficult for you to guess, but I'll help you. Imagine Michael is working with a very precious compound, okay? Something like a DEET analog that it has taken him like 2 or 3 months to figure it out. And he used a reagent that was like 50 milligrams was like $1,000. Actually, there was a molecule that we wanted that was more expensive. Like few milligrams was like $10,000 or some ridiculous number. And then they said that it may not be in good health by the time it reaches there. I said, we are not buying it. Okay. So imagine one of you or Michael or me have done the experiment and we want our compound back. Let's say we made like 30 milligrams and all 30 milligrams went inside your NMR tube, and which has an NMR solvent. We're going to discuss that later, maybe on Thursday. And it also has the internal standard. So I'm trying to drop a hint. So the internal standard, and at the end of the experiment, you want your compound back. You want your expensive compound back to do some other studies, not NMR, something completely different. So you need to get rid of the internal standard and the NMR solvent. And if there is anything else in there, probably not. So what kind of property should the internal standard have so that you can get rid of it easily? Let's say it's a liquid. What kind of liquid is harder to get rid of? Water, ethanol, nail polish remover, which has boiling point like 40 degrees or something, 30 something, or something like vegetable oil, which boils at 400 or 500 degrees centigrade. Which one is the easiest to get rid of? What property should it have?
Low boiling point.
Low boiling point. Okay. Anybody wants to throw an element that can be connected to the carbon, and then we can fill up the rest of the holes of the jigsaw puzzle. What kind of element can be attached to carbon to make a decent covalent bond, but that element will be very much like carbon, but it'll be less electronegative than carbon? What comes to your mind? You can pull up a periodic table and take a look at it. Something like carbon, and you have used it. If you have done some work on your bicycle or motorcycle or some lubricant, you may have come across that. And it's also used as part of an implants, all kinds of bodily implants. I'm hinting at a specific element.
So
Sorry, Isaac?
Silicone.
Silicon, yes. So if the hydrogen is attached to carbon and the carbon is attached to a silicon, silicon being right below carbon, it's also tetravalent. It does funny business, but generally it's pretty well behaved. Silicon's electronegativity value, I do not remember. I think it's 1.9-ish, if I'm not mistaken. So it's less electronegative than carbon. So the electron density is going to be pushed toward this direction. So now all you do is fill it up. So silicon has 4 bonds. Carbon has 3 bonds. So what will this molecule look like? CH3. CH3. You want it to be a symmetric molecule so that all the hydrogens have identical properties. They're all equivalent, and there are a whole bunch of hydrogens. Even though you're using like a tiny drop of this molecule, it's got a bunch of hydrogens, which is going to jack up the signal strength. Okay, even if you use a small amount, each molecule has 12 hydrogens. They're all going to show up at the same place because they're all equivalent. They're all the same. It's a symmetric molecule. It's a perfect tetrahedron. What should be the name of this molecule? The internal standard? Anybody wants to name it? Four methyl groups. It's going to be something methyl. How many methyls? 4 is written as what? It's a T word. Come on, guys.
tetra.
Tetra. So it's tetra methyl silane, SILANE. Okay, and it's called TMS. TMS. That's your internal standard. And it's assumed that wherever the TMS shows up, that's your 0 ppm. Okay, it's like we say where ice melts, that's 0 degrees centigrade, where water boils, that's 100 degrees centigrade. That's a preset number. Okay, 0. This guy shows up at 0 ppm, and everything else is calculated based on the delta E value of that guy. Whatever the delta E of TMS is, that's on the NMR spectrum, that's supposed to be 0 ppm. I think this is enough for today. I'm going to just let you guys go a little bit early. I don't think I am very tempted to take the discussion to the next level by discussing NMR solvents. I don't think I can pull it off. I don't want to rush it in 4 minutes. I would rather take time. Whatever I teach you, this is my teaching philosophy. Whatever I teach you, I want to teach you right. If you learn it the right way, then if there is something missing that you need to study before MCAT or PCAT, you can pick it up on your own, or you can come back to me and I'll be more than happy to go over that material with you. People have done that in the past. There was a gentleman named Abu Taha. He just kept asking me questions in a very nice way. He's in San Francisco Medical School right now. He's in San Francisco. He always had questions, and very, 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 very good questions. And he had nothing to make me happy about. So there were genuine questions, and we covered. I mean, we spent a lot of time. I mean, we even went out to the Starbucks in the library, and sometimes we spent hours going over some chemistry stuff. And I'm not saying that you have to do that, but I'm just saying that if you're missing something that we haven't covered because I spend more time delving deeper, then you can always come back, and my door is always open for you guys. Okay. If you do that, I might have come across a little mean in the last few days because I was really bothered with some of the business that's going on Canvas. I don't like it. Okay. There are too many of us are very privileged here, and we have many options. And even if somebody doesn't take the right honest path and takes the dishonest path, it really makes me mad. Okay. But generally speaking, if you're genuinely interested to learn something, it doesn't end at the end of the semester. You can always come back and you can ask me, and I'll be more than happy to go over anything that we haven't covered. Okay. So I think I wish to stop right now. We're going to catch up on Thursday. Okay. You guys have a good evening and good day, and continue to stay safe. I think there are signs of things not going down, new strains coming. So I'm going to take the picture. We'll make everything available as soon as I can. Have a good one.
Thank you.
Yeah, no problem.